Okay. The first thing I'd like to do in today's lecture is just go over very quickly how the grades are going to be posted along with the constructive comments. There will be a link in the table of contents, but it's not quite there yet. But there's a grades.html, and the way it will work is you'll type in your social security number in there, submit the ID, and it'll come out for your name, which will be posted there. It'll give a homework grade in red, and then there'll be comments regarding question 1 and 2. So there will be, 12, 13 homework grades, multiple question comments, some greater, some less detail. So that should provide you with some means of feedback for the various homework assignments. I think now that I'll perfect the system a little bit. I haven't done this before, but I think it will work for the class. Getting back to today's lecture, we finished the limits, part 3, last time in the previous lecture. And what I'd like to do today is talk about a closely related idea, that of functions. Now, functions, let me increase the size of this a little bit. Functions are, of course, a very early concept in mathematics, and we'll talk a little bit about how they arose, but the notation for functions is actually fairly recent. One of the earliest places where the modern f of x notation to denote function was found is in Euler, a manuscript by Euler in 1734. So I've included a nice little link here to the historical use of mathematical symbols. So for example, if you're dying to know who was the first person to use plus and minus signs, well, they've dated at least back to the early 1300s, 14th century. And they actually give the name of the manuscript and examples of the minus symbols first appeared in print in mercantile arithmetic. And I won't attempt to read the German there. So that's a nice little reference here. The function notation comes in with calculus. So as you know, Leibniz was the person who actually introduced the modern notation of dx, dy, and dy, dx. Newton was less concerned with notation. He kind of was an ad hoc approach to things. And it does say down here, Euler, let's see if this has here. We search for Euler. It's not in here. Okay, so this is a useful, here it is, various functions here, f of x. So the symbol f of x was first used by Leonard Euler in Commentary Academia Scientiarum Petropa Latine, butchered the Latin there. Okay, so those of you who want to go back to the original sources are welcome to read it in the original Latin. Now, there is a very close relationship, of course, between functions, limits, graphs, etc., and you can read about this in this site that I found. Now, it does have a nice little parenthetical remark that discusses how Newton and Leibniz actually viewed calculus and functions. It says in here that Newton had a much more graphical point of view of functions. So Leibniz was very much a notationally precise person, and of course his legacy is the integral sign and d and dx, other terms. They did not have really an idea necessarily of limits quite as we understand it, but we will discuss the relationship between functions and graphs in just a second. Now, We all remember the definition of a function in terms of sets of points, a range, and domain. So here is the current, or is a mathematically precise definition of a function. If you have two sets of points, a function is just a mapping or a rule from a set A to a set B, a relation it says here, so that for each element in the first set, there's one and only one element in the second set. So often you'll see this done in terms of a picture, intuitively. Of course, we have some set here that may not actually be in two dimensions, but we'll just denote it by A, and some other possibly different set here, B. If we have some element here, A, and some element here, B, F just takes this element and associates it with that element. And we write, of course, that B is a function f of A. So F is just a rule that associates members of two sets. The real requirement, of course, that we have is that you can't have, for a single valued function, you cannot have two b's, a b1 and a b2. So for single valued functions, and of course not all functions are single valued, but the ones we most often deal with are single valued. For single valued functions, you can only have A going to B, not A going to B1 and A going to B2. The consequence of this, of course, and that you've seen this as the very intuitive relationship between a graph and a function, is if you take and you graph a function, a single-valued function, it may have points of discontinuity, it may not even be defined for certain intervals, but if you take a vertical line, it can only intersect the graph of the function in at most one point. So here it'll intersect, say, in one point here, here it'll intersect here, etc. So the graph can only intersect at one place. So a vertical line for a single valued function intersects at most once. I should say at most, since it may not intersect at all. Okay. So we get back to the definition. It just, of course, takes, now the set A we all know is the domain, the B is the range, and we denote this by modern notation, actually due to Euler only 250 years ago, y equals a function of x. Or you can write it as an ordered pair, a set of ordered pairs, x being the first coordinate, f of x being the second coordinate, the result. Okay, so this is all very standard. Now, I have actually written for other purposes things that can graph functions. Now, this is an example of a Java-based applet where you can type in the name of a function and it will graph it for you. Actually, it even scales nicely, hopefully. Let's see if it'll fit in here. So this particular application you can type a function in here and you can graph the function. Of course, if you even have the ability to put in tick marks or not if you want. Now, the nice little thing about this is that I've made it so that you can actually zoom in on a function or actually move the function around. So it has a sort of a general utility here. That's getting kind of snarfled here. Well, here I've resized it. For example, you can investigate functions like sine x over x. If you graph this function, and let's change the range here, so zoom out here, so we can actually investigate this function. Actually, let's pick another one and reset it. Let's do sine of x squared. That's always an interesting function. And actually, if you zoom in on this function or zoom out on this function, you can see the behavior here. So this particular applet, all it does is graph a particular function, put some nice coordinates on, you can put some tick marks in, and actually this will, you can shift it to the left, right, etc. Zoom in, it has a bunch of different, zoom in on a point, and actually you can zoom, it'll zoom in on whatever is in the center of the point here, reset it. Okay, so it's clear that if you have a function, you can easily compute the graph of it. Now, of course, the graph of the function is exactly the set of points, is the set of all points x and y, two points, where y is related to x through the function values. Now the set of all x where f is defined is called the range, or excuse me, is the domain. And the image, or the set of all points so that y equals f of x for x in the domain, is called the range. So this is the domain, and this is the range. And we often write that the range is just f of the domain. So that means you take a point in the domain, it gives you a point in the range. Okay. So there are some more interesting relationships between functions and graphs that we'll get to in just a minute. The first one being the inverse functions. Now, what is an inverse function? An inverse function is related to f by the following. It's another function g with the following properties. Property 1, g of f of x gets you back to x, and f of g of x is equal to x. Now, if you remember the picture, of course, all this means is that if f maps a point x to y in this direction, then you can reverse that g, and this is often written as f inverse, f to the minus 1 power. G, if you start off with a point x and calculate y equals f of x and plug that into g, you just get back the original point. Also, this means that, for example, the range of f has to be in the domain of g, and the range of g has to be in the domain of f. So the range of f has to be in the domain of g. And similarly, the range of g has to be in the domain of f for this sense. Now, how do you calculate the inverse of f of x? Well, for simple functions, you can just solve it by the following. So if you have, say, y equals x squared plus 1, and this is f of x, what is the inverse? Well, if you just interchange x and y and then solve for y, so x minus 1 square root plus or minus, this is f inverse of x. And you can verify that they in fact have that relationship. So this trick of interchanging x and y and then solving for y will give you the algebraic form of f. It is also possible, as you well know, just by a simple manipulation to construct the graph of the inverse function even more easily than if you take a 45-degree line, and suppose we have, let's put it in blue, suppose we have a function that looks like this, then the inverse function, this is a set of x and y points, if we reverse the points, that is, reflect them about the 45-degree angle, this is actually the graph of f inverse. So this is the graph of f inverse. And of course, this is the graph of f. So the relationship between the inverse function f inverse and f is that the graph is just a reflection about the 45-degree line. Okay. Now often, if you take a graph and reflect it, you know what happens. Suppose you just take sine and cosine. This led to an early problem in functions. Let's get a little bit better here. Suppose you take the very common function sine of x. So I can draw this. Well, that's actually not the sine of x, that's the negative sine of x. So let's actually try to do sine of x here. Okay, so here is intended to be sine of x. If you reflect this about 45 degrees, what's going to happen? I actually even wrote that pretty well. Okay. If you reflect this about 45 degrees, it's going to oscillate in this direction and this direction here. So this is the inverse sine, and this is sine of x. So remember we said that a function, single-valued function, could only intersect the vertical line one point. So the inverse of this function sine is not a single-valued function. That's, of course, a problem, but one that was fairly easily resolved in the history of functions. Because what is one way to make the inverse sine of x single-valued? Well, one way is just to restrict the range between here and here, minus pi over 2, pi over 2. And let's do that. So if we restrict the range, and here's the inverse function here, and the inverse function here, between pi over 2 and minus pi over 2, inverse sine of x is single valued. Now, you could also tell that from the graph of sine of x, right? If we blew up the sine of x, let's draw it in blue here. If we only draw, that's not what I want, this one. If we only drew the first part of the function here, and the first part of the sine here, between minus pi over 2 and pi over 2, and this is 1, negative 1. So I guess if we enter, actually this should be 1 and minus 1, right? This should be 1 and minus 1. Yeah, we have to reflect this about here. Now notice that a horizontal line, if it intersects this graph only once, when you switch it, means that a vertical line will only intersect this graph once. So if you take a function that's a single valued, that furthermore has the property that a horizontal line only meets its graph once, then it will have an inverse function that's single valued. Okay, so this relates something that was very early known about the relationship between graphs and functions. Now, inverse functions, the question is when does an inverse function exist? And there actually is something called the inverse function theorem, or even the implicit function theorem, that tells you assumptions about when an inverse function exists. So the property, we saw F inverse, has the property that F of F inverse is F inverse of F, which is the identity X. And there are reflections about the line Y equals X. As it says, as noted by Feynman, F inverse is unfortunate notation because most times when you see -1 power, it means 1 over F, which is multiplicative inverse, right? So that's unfortunate, but what can we do? It's historical. Now, there are some rather deeper functions or deeper results that have to do with functions. Now, there's one called the implicit function theorem that asks the following question. And this was, again, one of the earliest questions that was asked for functions. It was a problem, if you will. So here's the question. If you're given a function of, say, 2 variables, x and y, and you want to solve this, so when is the solution of this function f of x y equals 0, when does this give a function y equals y of x? Or I should say, when does the solution of this give y as a g of x? So that means, is there a function g of x? Is there a g of x equals y so that f of x comma g of x is identically 0 for some x on some interval? For x on some interval. Okay. Now, this can't always be solved, right? You can't always solve an equation implicitly for one function in terms of the other. There's some actual conditions that have to be met. And this theorem can actually be found here. I found a link to it that wasn't too technical. Now this has to do with the implicit function in 1. So if you have a function, a multivariable function that maps function of n variables onto the real line, that means it's just a single real value, then you can solve that as long as the derivatives exist, the gradient doesn't vanish, and some other conditions here. And it also gives you conditions on tangent planes and the derivatives and implicit differentiation. If you have n variables mapping to m variables, then you have some more complications here. And this is the general inverse function theorem. Okay, so this is a nice result. And it actually resolved one of the earliest problems that people had when they talked about functions. This idea of open sets and their role in understanding behavior of functions and how it has to do with continuity, we'll talk about in the next lecture. So that was a topic I put in. Now, of course, remember what the definition of continuity is. Now, the continuity of a function of a single variable is quite easy to demonstrate. It results in checking several conditions. First of all, if a function is supposed to be continuous at a point, it should be defined there. Also, the limit as you approach that point from the left and right should exist. And finally, these should both agree. So, as we know, the idea of continuity has to do with the graph of the function. So if we have a function that has a jump in it, suppose it takes on this value and has a hole there. This function is not continuous because it fails at least one of those conditions. Now, first of all, the function is defined, right? If this is the point, say 1, 1, minus 1, f of 1 is equal to 1, that's because it includes this point here. And the limit, furthermore, exists from this side and this side. Both limits exist, but the problem is, of course, that the limit is not the value of the function. And that's why there's a discontinuity here. You can also clearly have a discontinuity for the following reason. You could have a function that just missed one point, had a hole in it, and then took the value up here. This means the function would be defined there. Both limits would exist from the left and right, but again, the limit would not be equal to the value of the function. So this is also not continuous. And of course, we have 1/3. And believe it or not, I mean, this all seems second nature to us, but back in the early days of functions, they were really struggling with questions. When is a function continuous? How many points can a function not be continuous at, etc.? Those were deep questions at those times. Okay, and the third way, of course, that a function can fail to be continuous is if it has a singularity. So, for example, you could have the function 1 over x, which looks like this, and that's, of course, not continuous at x equals 0, because it's not even defined there. Now, you should, as mathematics students, be aware of that any time you have a definition that involves multiple parts, those multiple parts are there for a reason. Namely that if 2 out of 3 of these are satisfied, or 1 out of 3, then it will fail to be continuous. So it's actually a good exercise to see how many different combinations of these things can be true with the remaining false. Okay, so there's actually continuity down here, and we know, of course, that the sum and difference, etc., of continuous functions are continuous, polynomials are continuous, e to the x is continuous, all that good stuff. Now, another property of a function, before we get down to the problems with the questions down at the bottom, was related to the differentiability of a function. Now, right after they defined the derivative, after Newton and Leibniz introduced the concept of a derivative in the calculus, there was a general question, is when is a function differentiable? And that's, of course, answered just by applying the definition of a derivative, and that means with a certain limit, f is differentiable at a point x equals a, if a certain limit of f of x plus, well, I guess a plus h minus f of a divided by h as h goes to 0 exists. And obviously this implies that f of a exists. And differentiability, as we know, is stronger than continuity. So if f is differentiable at a, then it's certainly continuous at a, but not the other way around. So differentiability implies continuity, but not the other way around. Now, it's an interesting question. Again, one of these problems that was looked at very early. And that is, can you have a function which is continuous only at one point? So the only question, and we'll pose this, so question 1, can a function be continuous, or be defined everywhere, but continuous nowhere? Well, we know that now, but this was a puzzle.
Rational indicator.
Rational indicator function. Okay, so a potential answer of this is just take f of x, which is 1 if x is rational, and 0 if x is irrational.
At first, I thought you said, is it continuous only at one point? That's what's revealed.
Yes, we'll answer that next. That's a slightly related question, but that also has an answer in the front of it. Yeah, let's ask this first question first and then return to the question of the continuity of single point. This is discontinuous everywhere because there are no 2 points that essentially share values that are adjacent to each other. So you don't have sequences of rationals which are contiguous or irrationals. This jumps alternately between 0 and 1. So it would be hard to graph this function. So the answer is yes. Now let's ask another question. Question 2 is, can it be continuous? Be f of x be defined everywhere, but be continuous at one point? In other words, be discontinuous everywhere, but except at one point. So only at one point. And the answer is yes. Does anybody have an example of such a function? Well, you can get it just by changing one character in this preceding function. And that is just change this 1 to be x. So if I change f of x to be x, if x is rational, and 0 if x is irrational, then the graph of it, so let me just make this a thick blue line. This will be the blue line for irrationals, and it will be this blue line for the rationals and irrationals, and they basically will meet here. So in fact, f of 0 equals 0, and it's continuous at 0 because if you approach 0 from any side, you can get within an arbitrary small neighborhood f of x equals 0. So in fact, the continuity of f, graphically, the continuity results because these two cross here, if you will. They don't literally cross because 0 is rational, not irrational, but the two graphs come arbitrarily close at the point x equals 0. So f of 0 equals 0 is the only point of continuity for this particular function. And f is continuous at 0. Now, there is a definition of continuity at a point that is the following, that f of x is continuous at x equals, say, a, if f of a exists and that's what we have here, and the limit exists and these two are equal. So if you actually pull that inside, you have the limit of f of x as x approaches a is equal to f of the limit as x approaches a, which is f of a. So this question about when can you pull the limit inside a function is resolved precisely when you have continuity. So continuity and limits are very, very closely tied together, as we all know. Okay, so let's go down to some of the other questions that were early on asked. Well, first of all, you can have functions of a single variable, functions of more than one variable, and discuss continuity. Now, questions of differentiability and continuity in more than one dimension are a little bit more complex, and you have to actually look at what you mean by distance and multiple dimensions, etc. If you go to a function of a complex variable, things get even more interesting, because what does it mean for f to be a function of a complex variable? Well, first of all, what is a complex variable? Well, we'll define it as a real and imaginary part. So we can have x and y axis, and this is the imaginary part, and this is the real part. I is equal to the square root of -1. And you can define a function f of z, say, as z squared. And that, as you know, can be expanded as x squared plus 2ixy plus iy squared. So this is x squared minus y squared, because I squared is -1, plus 2ixy. So the function has a real part and an imaginary part, just as x does, or z does. Now the question is when is a function of a complex variable, and this is a function of two variables, x and y, when is it continuous, when is it differentiable, etc. And that leads into a lot of questions that we'll discuss later on in the course for complex variables and analytic functions. So when is f continuous? And more interestingly, when is f differentiable as a function of two variables? So this leads to a very interesting area of mathematics called complex variables, or complex analysis, which we'll discuss a little bit later on, of course, because many, many mathematical problems were posed in this area later on historically. One type of thing that even further illustrates the relationship between limits and functions is the idea of extensions or closure. So for example, we might have a sequence of functions. Suppose we have f sub n of x as a sequence of functions. That means indexed by the real numbers. And we say, when does the limit as n goes to infinity of this sequence of functions make sense? That's not an obvious answer, because first of all, what do you mean by a limit? Well, a limit has something to do with distance, and what's the distance between two functions? So for example, and this is an important one, suppose I have f of n of x is sine n of x. If you graph that, what does this look like? This looks like a very solitary function for n large, but it always goes between +1 and -1, right? So does fn go to 0 in any sense? Does fn approach a function in any sense? What is the sense that limit of fn as n goes to infinity of this sequence exists? And the answer is it does go to 0 in a sense, but you have to be precise about that. So we'll talk a little bit. Now, if the sequence of functions exists, well, another way to examine limits and functions is the question is, suppose f is defined on an open set. Let's ignore right now what the definition of an open set is, but suppose xn is in this open set O, and xn approaches a limit A. A may not be an O, right? It could be O may not contain its limit points, right? And it's not closed, it's open. So how would you define the limit of f of xn as n goes to, well, I did it backwards. How would you define f of a? Well, you would define it, one way to define it is to define it as the limit of these points, the limit of the function values as xn, as n goes to infinity, xn approaches a. So if f were to make any sense at all, now bear in mind that a might not be in this open set. It might not be. So the question is if you have f defined on an open set, how do you extend it to all the limit points? And the answer is just by the simple limit extension. So we extend f to a bigger set, to what's called the closure of O. Now, this can be quite a large set because, for example, suppose you have f defined on a set of rational numbers. How would you extend it to the real numbers? So, for example, if f of x is equal to x, for x is irrational, but not defined on This is what I mean by extension or closure. Now this can lead to a lot of interesting questions that we'll get to next lecture also. So this leads to all kinds of very subtle problems. Now here's a set of questions that came up very early on historically having to do with graphs and limits. And the first one is every function continuous except an accountable number of points. Now countable means that you can index them by the natural numbers, 1, 2, 3, etc. So let's look at the first question here. Is every function continuous? Except a countable number of points. And what do you think the answer to that is? Can we make every function continuous just by fixing up its values at a set of points indexed by the natural numbers?
I know that the rationals are countable, and if you would pull them all out of that indicator function, I would think that it would be continuous, but if you do it the other way around, it's not necessarily true, right?
So the question is, can you construct a function that's actually, which is discontinuous, say, on the rationals? Or say irrationals. In other words, can it jump around so that between any two irrationals arbitrarily closed, it basically oscillates around incredibly fast. So you can't actually graph it. Now, this is where your intuition leads you astray, because when you're graphing functions, you can only draw essentially countable numbers of discontinuity. So if you put in a function with a hole here and a hole here, even if the holes kind of pile up, like, for example, f of x is equal to 0, say when x is equal to 1 over n, and then f of x is equal to 1 otherwise. This again has a finite number of discontinuities, points 1 over n. It's equal to 1 for most values of x, but for an infinite number of x's piling up at the origin, it's not continuous. So the question is, this is a countable number of discontinuities. Can you construct a function which is discontinuous at all irrationals? And the answer is yes. And I'll let you think about it for next time, and then we'll discuss it. In fact, this question had to do with the very foundations of integration, because a necessary and sufficient condition for a function to be Riemann integrable is that its set of discontinuities essentially be a set of measure 0, and a countable number of points is a set of measure 0. So there is actually a deep relationship between this point, and actually let me just extend it, countable number of points by a set of measure 0. It anticipates the next lecture a little bit. Is every function continuous except for a set of measure 0? And the answer is no, because if a function is continuous except for the measure 0, it would be Riemann integrable, and not all functions are Riemann integrable. Okay, so we'll get to that. So this was answered in a way in the negative, but it actually had to do with some very deep relationships between continuity and integrability. And that's the second question here. We already know the answer to this. We had the example earlier. Is every function differentiable except for a set of measure 0? This was widely believed early on that it was true, that every function was essentially differentiable, because when you graph functions, you essentially tend to graph things in a very smooth way, and so they thought even if it's discontinuous, you can just throw away a point or here or there, and you can make it smooth. So the answer is, again, no. Not every function is differentiable except for the measure 0. The Weierstrass function actually is a case of a continuous function which is nowhere differentiable. Another very deep historical question that relates to this idea of a limit of functions is, if you have all of these functions continuous, is the limit of a sequence of continuous functions continuous? So is the limit of a continuous sequence of functions, I should say sequence, functions continuous? And of course we know that the answer is what? The answer is not necessarily. Yes, there's a sufficient condition, not necessary, but sufficient, of uniform. If it converges uniformly, it will be continuous. Okay, so, and again, you can get an idea about this by graphing, because this actually led to a stronger definition of uniform continuity that we'll talk about again in the second lecture. So problems such as these, like is every function continuous, or is every function differentiable, or is the set of bad points countable, actually led to very deep results in differentiability of a function of complex variables, led to the whole subject of analytic function theory. Example, extensions and enclosures essentially led to a whole area of analysis, functional analysis. The investigations of open sets led to, of course, the whole subject of topology and metric spaces. Questions of sets of measure 0 and continuity led to the very foundations of what we understood as integrability and the limits of Riemann integration and its extension to Lebesgue integration. And the idea of differentiability led to extensions of differentiability, such as Guattari derivatives, Fréchet derivatives, other kinds of derivatives. And particularly in multiple dimensions, or even infinite dimensions. And the idea of limits of sequence of functions led to just whole realms of analysis. So the very simple ideas of functions at the very beginning, just as relationships between sets of points in the domain and the range, quickly led to some very subtle problems, the resolution of which led to some of the most interesting areas of mathematics that we had studied, namely topology, complex variable, real analysis, functional analysis, differential equations, analytic function theory, integration, etc., the Lebesgue measure theory. So we'll go into some of these ideas, obviously not at great detail, but I'd like to go and show you where some of the questions about behavior of functions led to some very, very interesting realms of mathematics, and I'll try to put it into some historical context. So just to summarize, the idea of open sets, let me change pens here. So open sets and the idea of distance led to a whole area called topology. The differentiability of functions of a complex variable, f of z, leads to complex variable theory. The whole idea of limits of sequences of functions in closure leads to real and functional analysis. The idea of measures and leads to the idea of Lebesgue integration. The idea of is a function continuous almost everywhere, or everywhere except to the measure 0, leads to the fundamentals of Riemann integration. So the discontinuities and the measure leads to very deep questions of Riemann integration. One is a function Riemann integrable. So we have just huge problems that are of enormous interest. We've got topology, complex variable theory, real and functional analysis, Lebesgue integration, Riemann integration. So there you have your written qualifiers pretty much, except for number theory and combinatorics and algebra, just on the basis of describing what is a function, when is it defined, for what sets it's defined, how do you find the inverse of a function, when can you differentiate it, when can you integrate it, when can you take a limit. These are just very fundamental questions that were, of course, asked almost as soon as they could be asked intelligently, and the resolution of some of these took many years and led to the creation of many, many of the basic areas of mathematical analysis. So we're not going to cover that in 10 minutes, but we will at least begin talking about some of this next lecture. So I'll take